So let's do what will be our usual setup with omega fp being a probability space. Omega is the sample space, F is the sigma algebra, and P is a probability measure. And then recalling the setup from last time, the script B is going to be another sigma algebra on omega, possibly different from F. And it will have an associated partition. And we discussed how to get this partition last time. The partition we'll usually call capital pi. It's a collection of sets, f sub I, for I in some index set, usually finite or countable. So this is our setup. And a while back, we discussed how to get from a partition to a sigma algebra, and then more recently from a sigma algebra to a partition. One of the ideas is that to go this way, from the partition, we use the sigma algebra generated by this collection of sets. And then for the other way, the overall idea is that these f sub i's are the smallest disjoint sets that cover omega. Okay, so now, with this setup, let's define what a conditional probability is. So if A is a subset of omega, then the conditional probability of A with respect to B, now B is script B, the sigma algebra. So WRT is short for with respect to. So the conditional probability is a random variable. And we're going to give it the name P of A, and now a double vertical bar. So conditioning on the sigma algebra B. So remember last time we had P of A given B, and this B was just a set. Now this double bar is meant to signal that this is different. This is now a sigma algebra script B rather than just a set. Okay? And this also makes sense because the different notation makes sense because when we defined this probability, it was the ratio of two other probabilities, and that's a number. But this new thing is it's not a number, it's a random variable. So it's a more abstract object. And which random variable is it? Well, we're going to observe in a minute that it's constant on each set of the partition, f sub I. And it's defined by, here's the formula, P of A given script B of omega. So it's a random variable. So it depends on which point in the sample space we're looking at, which outcome. And this random variable is defined to be P of A given f sub I, the old conditional probability for conditioning on a set if omega is in f sub I. So this P of AB is a random variable that takes a whole bunch of different values. Those values are these values so this is a random variable that depends on I. So let's do an example to illustrate this. Let's say we flip 2 fair coins. And let's let script B be the following sigma algebra, that it contains the empty set. Then it contains 2 outcomes lumped together, where the first coin is heads. Let's call this set F1. And then it contains also the complement of F1. Let's call this F2 also, and all of omega. And we know for 2 fair coins that omega is ht squared. We've looked at this before. So now with this particular sigma algebra, script B, let's discuss what the conditional probability is. So A is implicitly any subset of omega. And okay, so here is how I'm thinking about this. So if A is some subset of omega, then what is the conditional probability of A given this sigma algebra B? So we can use our definition. There is the probability of A given, well, first we should figure out what these f sub i's are. I already told you, kind of gave it away. F1 and F2, these are disjoint sets, and they cover omega, and they're the smallest ones in this setting. So this is our partition. Pi is F1, F2. So now we need the probability of A given F1 if omega is in F1, and the probability of A given F2 if omega is in F2. So let's compute these probabilities and figure out what probability they happen with. Because this event, omega being in F1, happens with some probability. Which probability is that? Well, what's the probability of having the first coin be heads? It's 1/2, and we don't care what the second coin does. So this happens with probability 1/2. And so this WP is short for with probability. And similarly, F2 also happens with probability 1/2. So what are these values? So P of A double bar B is a random variable. P of A bar Fi is a number. And which number is it? Well, so we can use our definition of conditional probability from last week. This is the probability of A intersect F1 divided by the probability of F1. And so probability of F1 we just discussed is 1/2. So this is 2 times the probability of A intersect F1. So if we knew what A was, then we'd be able to say what this probability is. And let's consider this particular A. By the way, the same formula holds for F2 in place of F1. there, so we can actually write this for I. And so now, what if A is a particular event? Let's say A is the outcome where both coins are heads. Then this conditional probability, P of HH given double bar given B, is what? Well, we need to compute the probability. If we put in A here, the probability of HH intersect Fi, well, for F1, this is just the probability of HH because HH is a subset of F1. So this is 1/4, I believe. Oh, wait a second. Oh, that's right, yeah, because then we multiply by 2 and we get a half. So this is 1/2 if omega is in F1. And then what is it if omega is in F2? So we need to know the probability of HH given F2, which is TH and TT. And what is this probability? 0. So that 0 goes here. And we're done. Now, this conditional probability, given the sigma algebra, is a random variable that takes two values, 1/2 or 0, each with probability 1/2. Okay. Now, here is an observation. First of all, that the probability of A itself for this particular A is 1/4. And that part's not quite so interesting, but there's another way of computing this P of A. The law of total probability tells us that the probability of A is also the probability of A given F1 times the probability of F1 plus the probability of A given F2, probability of F2. And then we have these values here. So P of A given F1 is 1/2. The probability of F1 is 1/2. Then the probability of A given F2 is this 0. And the probability of F2 is also 0. But this gives us 1/4. So this is an example of the law of total probability in action. Questions?
What's that mean? You have two errors, each with probability 1/2. What's that mean?
Yeah, it's just repeating what I wrote up here, that these happen with probability 1/2. And I didn't want to go over this line, but that's what it means. Yeah. Other questions? Okay. So now we're about to define expectation or expected value for a random variable x. And then we'll get to the conditional expectation. The conditional probability with this double bar is a random variable, and so is the conditional expectation of a random variable given a partition, given a sigma algebra. Question?
So the purpose of defining this new random variable by using double bar is
because like we just want to partition this understanding into two partitions or many partitions, so now we can talk about which.
Okay, so Yufan, right,
Yes.
is asking about the purpose of this conditional probability
Because
given.
it's not really about the sigma algebra. Actually, we care about only about partition, right?
But remember, the sigma algebra and the partition are equivalent to each other. So it doesn't matter whether we're, in fact, in other notation, you can put a partition here. And it's the same idea. Because of this correspondence between partitions and sigma algebras. But let's go back to your real question, which is the purpose. Well, what is the purpose of this? This B, the sigma algebra, gives us partial information about the underlying random variable. And so we can refine what we know about an unknown event A based on some partial information B. So for instance, one place where this is useful is where the partial information is what happens to the first coin. Well, if we're interested in the outcome heads, then partial information actually guarantees us the probability that HH given F2 is 0, which is very useful information. And more generally, sigma algebras like this or partitions give us partial information about random variables.
I thought this was conditional probability is supposed to do, like, that's.
They both do this. Conditional probability, whether you're talking about double bars or single bars, they both give you partial information.
Okay.
Yeah. And this is properly speaking a collection of partial informations, of which each one of these individual ones is a single nugget of partial information. So this systematizes our partial information. So we'll be revisiting this idea of partial information over and over, especially in the next section after expectation, where we talk about filtrations of sigma algebras. But we'll be getting to this, and we'll see the idea of partial information coming up over and over. Okay, so we have our usual omega fp, a probability space. And we're also thinking of an index set, I, together with its power set as its sigma algebra. And then, so the expectation, or expected value, of x, which a random variable is a map from omega to I, is defined this way. It's written in notation as this blackboard bold E of x. And it's defined actually possibly two ways. And these two ways are related to two notions of integration in real analysis. Perhaps those of you familiar with real analysis will be able to see this analog. So one way of defining the expectation is by taking the sum over the sample space, omega, of x of omega, the particular realization of the random variable x, times p of omega, the probability of getting that outcome. So this is one way of defining expected value, and it's equivalent to defining it the following way. So I'll put this colon in front of the equal sign to indicate this is also a good definition. So this is another way of defining it by summing over the index set I, the value I, times the probability that x is equal to I. And those of you who have taken undergrad probability with me have seen this definition before. It turns out to be equivalent to this definition. So anybody who's taken analysis, can you describe how these are like two different ways of integrating? This is extra special bonus material. I will not test you on this.
it just grouping?
It is grouping things in different ways, but we have fancy terminology for this in real analysis.
There's a one-to-one correspondence between I and omega.
So the question is there a one-to-one correspondence between I and omega? Not necessarily. X can collapse things from different points of omega to the same point of I. So there's not a correspondence, but these sums, the sums wipe out. We don't care if there's a one-to-one correspondence. The sums take care of that. So the sums are the same. Shall I just give you the answer, or anybody else want to?
It's kind of like a Lebesgue measure. You know the value, and then you know turn back, you know the domain of things.
Yes, exactly. It's a lot like a Lebesgue measure. In fact, this one is like the Lebesgue integral. And the first one I wrote down is like another integral, the Riemann integral. So the Riemann integral is integrating by summing, summing is a lot like integrating, summing over all the values of the argument, whereas Lebesgue is summing over all the values of the function. So two different ways of adding up. It's basically rearranging, and you get the same answer, but sometimes one of these ways will be more convenient to compute with, and other times the other way will be more convenient. And you can learn by practice which one might be more useful in a particular setting. Okay, so that was the comparison with these integrals is kind of an aside, although we will in practice see a little bit of this. And I also want to define the expectation of a function of the random variable x. Because when we get to variance, we'll want to compute e of x squared. And in general, we can do the function of any function of a random variable. And this is defined, let's do this just like the second one, as the sum over I of f of I times the probability that x equals I. Okay, so here's a nice theorem that expectation is linear, and what this means concretely is that the expectation of a sum of n different random variables, so sum of xi, of I from 1 to n, is equal to the sum of the expectations. So expectation is linear means that we can trade the order of summing and expecting. We can either, this is x sub I in this sum. So we can either sum the random variables first and then take the expectation, or we can take their expectations first and then sum. This is exactly analogous to the linearity of integration in calculus. And we can prove it. So here's how this goes. If we look at the left-hand side, LHS is left-hand side. So we have the expectation of a sum of random variables. So let's use our definition of expectation to write down what this means. We're going to be replacing x in this formula by the sum of xi's. And so let's use the omega part of the definition. So this is the sum over omega. We're going to put our xi in the parentheses and then times p of omega. So sum of xi, I from 1 to n. And there's an omega hiding here. So this is the definition The sum of random variables is a new random variable, and we're plugging that new random variable in for x. So we get this double sum. A classic thing we do with double sums is we switch the order of summation. And this is legit because one of these sums is finite, so we can reorder the sums because one is finite. And when we do that, we get the sum over I from 1 to n of the sum over omega of xi of omega p of omega. And now what can we do with this? So we have a new double sum. Our goal is to get this right-hand side. So how can we get from here to there? Group it. So let's look at inside the parentheses. And this is now, going back to look at our definition, this is exactly this expression inside the parentheses, except with xi instead of x. So that tells us that this inside the parentheses part is, okay, so we have our sum on the outside, I from 1 to n, and then the inside is exactly e of xi. And so that's how we prove linearity of expectation. Questions?
Can we use Fubini theorem to extend it to infinity?
Can we use Fubini to extend it to infinity? Quite possibly, yes. There might have to be a little bit careful about convergence and so forth. If we run into that, we'll be careful. Okay, so linearity of expectation. Now we talked about independence of events. So two events, A and B, are independent if and only if P of A intersect B is P of A times P of B. So this product form for probabilities and events. And now we're going to talk about independence for random variables. And the idea of independence for events extends to independence for random variables as follows. So we've got two random variables now, x and y, and we say that they are independent if and only if for all I and j that the probability that x equals little I and y equals little j, this comma means and, that this probability factors into the probability that x equals little I times the probability that y equals little j. So now, these x equals I is an event. It either happens or not in the sample space. And y equals j is also an event. So we're just applying the idea of independence for events to events that involve x and y. And now this tells us something about the expectations of x and y. But there's a little caveat here. So here's the fact that you may have seen in another probability course. So if x and y are independent, and by the way, the opposite of independence is dependence. But if x and y are independent, then the expectation of x times y is, it does factor like you might expect it to. It's the expectation of x times the expectation of y. So if x and y are independent, then the expectation of their product is the product of their expectations. If, but not the converse. So this idea of the expectation factoring over two random variables, actually you can define it to mean uncorrelated. And we're using a different word from independent because it turns out uncorrelated and independent are not the same thing. But not the converse. And we'll skip over the proof. You can do it as an exercise. If you try to do this, I encourage you to use the I version of the definition of expectation, so the Lebesgue type. And then the proof works pretty nicely that way. So anyway, the point here is if x and y are independent, then expectation factors, but not vice versa. You can come up with an example of two random variables whose expectations do factor this way, but these random variables are not independent. They are, in fact, dependent. OK, so now that we've defined conditional probability and expectation, now we're going to define conditional expectation. So let's say we have a random variable x, which is a map from omega to I. And say we take an event b, so a subset of omega. This event is going to be the event that we condition on. So like before, we need the probability of b to be positive. Otherwise, we'd be dividing by 0, and that wouldn't be good. So the conditional expectation of x given b is a random variable. Gesundheit. Actually, it's a number. The conditional expectation of x given a sigma algebra script b will be a random variable. And expectation of x given just a simple event b is defined this way: the sum over I and I of I times the probability that x equals I given b. So x equals I is an event. We can take its conditional probability given b. And another way of writing this is the sum over I of, now we can use our conditional probability definition here. So this is the probability of x equals I and b both happening, intersect, I guess. And let's put braces on this to make it clear it's an event divided by the probability of b. So that is conditional expectation. And questions so far?
I have a question about the expectation of xy. We have the exponential of x and exponential of y, and their product factors into expectation of exponential x and expectation of exponential y. Can we conclude that xy are independent?
So you're adding an extra layer of complexity here by talking about exponentials of random variables. And this is not something I want to get into yet, but what you're actually talking about is the characteristic function or the moment generating function, one of these. And those are really nice ways of characterizing random variables. I'm going to skip answering your question for right now, but that's an interesting question. Okay, so what kinds of objects are these? We've talked about this a little bit, but let's kind of clarify, systematize what these objects are. Scalars, functions, random variables. So P of A given B, P of A given script B, expectation of A given B, and then in a minute we'll define expectation of A given script B. And just to make things extra confusing, we're only going to use one bar here instead of two. You're welcome to use two if you want to. Okay, so what kind of object is this first one? Number. It's a number or a scalar. The second one, we talked about this earlier, is a random variable. We just defined the expectation of A given B. It's a sum of some ratios of numbers, so that's a number. And then in parallel, you might expect that the conditional expectation of A given a sigma algebra is also going to be a random variable. Okay, so now we're going to define this one. And again, you can use the idea of the sigma algebra script B containing partial information, and then from that partial information, we can refine what we might expect to happen for an event A. So the usual setup, x from omega to I is a random variable, and B is a sigma algebra on omega. Another sigma algebra, aside from the script F. So, and let's say it has a corresponding partition, capital Pi. Collection of F sub i's. And then the conditional expectation. And by the way, I will often abbreviate conditional this way. It gets long to write out. And expectation, I'll often abbreviate just as exp. Not to be confused with the exponent, but if it's ever confusing, let me know. So the conditional expectation of x with respect to script B is a piecewise constant random variable. So that's a lot like this conditional probability. This was also piecewise constant. Defined by E of A given script B. This is a number that depends on which outcome in the sample space we're looking at. And it's a number that depends on the outcome, hence it's a random variable. So this random variable for omega is defined to be E of x given fi if omega is in Fi. And the idea, again, is that the script B gives us partial information. So let's do some examples. So first of all, these are kind of general examples. So the coarsest sigma algebra on any sample space omega is what? So let's give it a name. Let's call it B sub C. What is the coarsest sigma algebra on any space? Empty and the whole set. Coarse means the sets inside this are very large, and indeed omega is very large. Of course, we throw out the sample set, throw out the empty set when we talk about this. And the corresponding partition is just omega. So pi is simply omega, only one block in this partition. And then what is E? Oh, there's a typo here. A should be X, thank you. And I borrowed that typo from over here. These really should be X's. We take probabilities of events and we take expectations of random variables. Just to further confuse matters, later we can talk about random variables that are called A, but for now, let's call our random variable X. And what is E of X given this BC? E of X, how did you get that?
So one is always belongs to this.
Right, so let's use our definition. We'll fill in a step to clarify this. So the definition tells us, okay, we could put in an omega here, but we can also skip it just because, oopsie, this is omega. So our definition tells us E of X given BC is E of X given omega, because that's the only Fi. And all of the omegas are in this Fi, which is omega. So there's only one case, only one thing in the partition. That's E of X given omega. And what is E of X given omega? We would have to go back over to this definition. If we put in B equals omega, well, this probability is just P of X, or P of X equals I. Because omega actually gives us, remember the idea of partial information, B is partial information. Omega is actually all the information. So when we have all the information, we're divided by 1 here, so you can compute that out. And this is exactly E of X. Actually, I misspoke a moment ago. I said omega has all the information, but actually, this sigma algebra BC doesn't distinguish between any points of omega. It lumps everything together. So actually, it's better to think here that omega, that this BC has no extra information. So our best guess for E of X given BC is just E of X. There's no extra information in BC. So I'm trying to give you the intuition as I prove these things. I hope that's helpful. And so that's example 1, where the partition is just so coarse that we don't get any more information. What about the opposite extreme, where the partition has all the information in it? So the finest sigma algebra What is it? The power set, yes. So BF, F for fine, is 2 to the omega. This is the set of all subsets. And so pi, the partition, is what? These f sub i's. Sorry, suddenly I'm switching to I in my notes and looking at the reason for this. So actually, I want to take okay, let's actually look at 2 to the I. So we're talking about partitioning the target space. X is a random variable map from omega to I. And then what are the sets f sub I in this partition? Now, for those of you who might be a little confused by this switch, X is a map. So we can move sigma algebras from one space to the other, and possibly vice versa. So that's what I'm doing here. And now the partition for the index space, I, is going to be a set of singletons. So each I is separate. And then when we compute this random variable, E of x given BF, what do we get? So we need E of x given Fi if omega is in Fi. But okay, so x is a map from omega to I. So I think this is what we need here, that x of omega is in f sub I. And then, so this is E of x given the singleton I. And if that's the case, let's use this definition of conditional expectation. So this gives us a sum. Okay, we have an I here, so we need a different letter to sum over. Let's call it J. So we're summing J times P of x equals I given I. And now what is this probability? Oh, there's a typo. So if we're summing over J instead of I, then we need J to be here too. So this is actually a J. So now what are these probabilities? Well, they're either 0 or 1. And this is equal to 0 if J is not I, and equal to 1 if J is I. So really, the sum is just a single term, the ith term, I times the probability, which is equal to 1. And so the expected value is the I that x is equal to. And another way of writing this is x of omega. By, see, we've conditioned on x equals I. And so that x is that I And this happens if omega is in Fi, if x of omega equals I. So this sounds kind of circular, but this is because the sigma algebra and this partition Fi have all the possible information we might want.